Well, thank you very much for the opportunity to be here. My name is Fabiano Ribeiro, and I present the work that I have developed with my friend Diego Heibske about mathematical models to explain the urban scaling law. So here we have GDP as a function of the population, and every point here represents one city from USA and from Brazil. And this straight line here in the log-log plot means that this data can be described by the power law like this one, with exponent greater than 1. That means that when you increase the size of the city, you also increase the GDP per capita. That means that larger cities are richer, right? And on the other hand, you have other kinds of variables that also behave like this one. For example, the number of mobile phone contact per capita also increase with the population size. That means that the larger city, the people have more mobile phone contacts as well, right? On the other hand, there's other kinds of variables usually associated with infrastructure that will have what we can call the sublinear behavior, because when you increase the size of the city, you decrease per capita number of this infrastructure variable, right? That means that larger city need less infrastructure per capita. And other kinds of variables that also behave like, in a nonlinear way is the fundamental allometry that is about the area of the city in relation to the population size that also behaves sublinearly. So to sum up what I mean, what usually is called the urban scale theory or the urban scaling idea is that we can divide the urban metrics, the urban variables, in 3 categories. One associated with infrastructure that have beta, that the scaling exponent that smaller than 1. Other individual basic service that have beta is equal to 1. That means that you have a linear scaling between these metrics and the urban and the population size. And the socio-economic variables that have a superlinear behavior. That means that you have beta greater than 1, right? But how does this urban scale emerge at all? To try to answer this question, I and my friend tried my friend Diego tried to organize all the models that we have in the literature, all the models that have some kind of mathematical approach, some kind of quantitative approach, in order to explain urban scaling as an emergent phenomenon, right? And organizing these models, we could build up this taxonomy here that we can divide the models in the inter-urban process kind of model and inter-urban process kind of model, right? Here we have also the prevalence. You have models that try to explain socioeconomic urban scaling that is based, for example, in collaboration, gravity idea, infrastructure, geometry, diffusion of technology, all these kind of things that try to explain socioeconomic output, right? And also you have other kinds of models that are restricted to try to explain the fundamental allometry, infrastructure, urban scaling, and so on. The main concept to explain the urban scaling present in this model that refers to is about interaction between people. I think that the most common concept present in all this model, or not all, but most of this model, is about the interaction between the people. So the urban scale is a multiplicative combination of population, density, geometry, in order to interfere or enhance or disfavor the interaction between the people, right? And basically, in the case of socioeconomic output, there is a general approach here. And for example, the idea is that the model proposes a density of contacts. That means the number of contacts in relation to the population size. So when I multiply by n, we have the number of contacts that one single person have. And if I multiply by a constant that, or not a constant, or a function that represent the output from one interaction, we have the total socioeconomic output of a single person. Then if I multiply by n, of course, I have the total socioeconomic output of the city, right? So what defines the model that try to explain the socioeconomic urban scaling accord with the consider the interaction between the people much to modeling the density of contact. That is what defines the model. So, for example, the idea is that if we have this empirical evidence here, that we have a superlinear behavior between the socioeconomic output and the population size, the density of contact must obey this relation here, this parallel relation here. And that's exactly what all of this model try to do, right? For example, in the case of Bittencourt model, you have the idea of cross-section between the movement of the people through the city, and the density of contact is computed given the ratio between the area assessed to the one single individual and the total area of the city, or more specifically, the area of the infrastructure, the area assessed for the people, for one single people, in relation to the area of the infrastructure area, right? Or in the case of the gravity models, that the interaction happen in pairs, and the intensity of this interaction decay with the distance according with this quantity here, according with the power law, where gamma is the parameter that governs the range of interaction between the people. And we have other model that I'm called here Penn et al. Model, that is a kind of particular case of the gravity model. And what is interesting about this model is that the idea is that you consider homogeneous distribution of the population, and the interaction happen with a gamma is equal to 2. That is precisely the Newtonian kind of gravity model. And what emerged from this calculus here is not a parallel, but in fact, not a parallel relating socioeconomic output and population size, but instead of that, what come out is n multiplied by log n kind of equation, right? And what is interesting is that when I plot, for example, the power law here in the blue line and the n log n in the red line here, you can see that both of these equations is good enough to describe the empirical data, right? So, and to finalize here, we have the Molinero and Tanner model that consider an interplay between the fractal dimension, or the fractal distribution of the population, and the fractal dimension or fractal distribution of the infrastructure. So the probability of interaction is the interplay between infrastructure and population spatial distribution, right? And what was interesting also when we put all together these models is that we could compare very different kind of model. For example, we have here the Bittencourt model that is considered the idea of the cross-section interaction of the people, and they also consider that the salary must guarantee the access of the city, access of the people throughout the city, and you also have the Luft and Bartholomew kind of model that consider the resilience of the transport network to congestion, and the arriving of multi-center. And that is, these two models are completely different in kind of hypothesis, right? But if I identify that df, that the fractal dimension considered in the Bittencourt model, is equal to 2 times the resilience of the transport network considered by Luft and Bartholomew, in fact, the value of the beta for both superlinear scaling, sublinear scaling, and also linear scaling also have the same result, right? So that means that both of these models conduct the same result, the same output. If I even that they consider different hypotheses, initial hypotheses, right? Now, in the case of the gravity models, you also try to find some general idea that all those others gravity models can be interpreted as a particular case, right? The idea is that I need to compute a number of contacts that the people have. We have here the probability of interaction, that is the gravity idea, right? The k with the distance, and the spatial distribution of the population, right? If I can compute that, the number of contacts, of course, I can get the density of contacts given by that, and also I can compute the socio-economic production of a single individual, given that we have G here that is output of a single output generated by socio-economic output generated by the single interaction, right? And then I can get the socio-economic output of the city, right? So what distinguishes the models is about how they given or approach the value of this quantity here, the probability of interaction, the socioeconomic output of the interaction, and the spatial distribution of the population, right? For example, in the Ribeiro et al. Model, the model that I have proposed, we consider this kind of probability of interaction. We didn't consider that all the interaction product the same socioeconomic output, and we consider also the fractal distribution of the population, right? Or in the case of Jacobo et al. Model, that consider that the interaction not only happen according with the distance, but also according with the influence of the people. So there is a distribution of the attractiveness of the people, and then that is a new ingredient for this approach. And also that the socioeconomic production of a single interaction depends on the distance of the people, right? Also, you have Arbersman et al. Model that considered not Euclidean distance as the interaction, right? But in fact, they consider the socioeconomic distance, the social distance between the people, right? And Penan, that I already talking about, is a particular case here as well. So you can get all this model here using this general approach for the gravity model, right? And what I think that the main, most important output of the gravity model is that we can predict the value of the beta according with the geometrical properties of the system. For example, in order to have a superlinear scale is necessary, according with the solution of the mathematical approach of these gravity models, is that we need to have a long-range kind of interaction. That means that in order to have a superlinear scaling, the gamma value, the gamma is the parameter that governs the range of interaction, must be sufficiently small. And sufficiently small according with the fractal dimension of the population, of the distribution of the population. And in addition to that, we can write or can get as an output of the models is that the beta test, the urban scale, can be determined by this gamma, the range of interaction, and also the fractal dimension of the population, right? And other properties that have emerged when they put all this model together and see the big picture of this model is that the integration of the city as a whole is the main ingredient to have increased return to scaling in order to have a superlinear scale, in fact. For example, in the case of the gravity models, it's necessary to have long-range kind of interaction in order to have a superlinear scaling, right? And also, Bittencourt model only can explain superlinearity when he imposed that salary of the people must guarantee access to the entire city. And Luther and Bartolomé model have also the same idea. According with the distance people can travel must be sufficiently large in order to guarantee the city's integrity. So the main result here is that we have different kind of models, but all of them get the same result, that we must to integrate the city. So the superlinear scaling is in fact a consequence of people that are integrated, is completely integrated in the city in order to have a socioeconomic production that increase with the size, right? And only to finalize here, we have the other parts here of the model that is just a small part in comparison of all the models that we have present in literature, that you have models that are that consider interurban process, so exogenous process, in order to explain urban scaling. You have, for example, the diffuse of technology of women that consider that technology arrive in large city and then spread to a small one. That is the qualitative explanation for Pullman to superlinear scaling. Or you have the aggregate scaling that try to, for example, here in the Haroldo Ribeiro et al. Model that consider that superlinearity is in fact a consequence of the Zipf's law. Is a related phenomenon. Urban scale is a related phenomenon to the Zipf's law, right? So, in order to finalize, I want only to emphasize 9 unsolved problems of the urban scaling. Of course, I don't have time to talk about all these 9 unsolved problems, but I need to mention the necessity to a well-defined definition of the city boundaries. So we seeing a lot of work that depend of the city definition. You have different scaling exponent values. We need also to solve the problem of longitudinal and transversal scaling. That means that what about one particular city? When the city growth, this city behaves in the same laws that we have observed here in the system of city. That is one question that must be solved. And of course, urban scale is just a part of the big picture of the city, right? And if we want to get a new science of the city, we must to have a more general approach, a more general theory that urban scale is just a particular case, right? So we need to try to increase the scope of this theory, not only about urban scaling, but we need to get a more general theory of the city, that urban scale is just a particular case, right? So that's my collaborators, my team, my colleagues, my friends, students, and that's the financial support. Thank you very much for the opportunities. Well, thank you.